In this video, we're going to discuss algebra operations applied to vectors. So we have two principal operations involving vectors, and those are vector addition, meaning we can take two vectors in component form and add them, as well as scalar multiplication. A scalar is a real number. A scalar can be positive, negative, or zero, and they are used to scale a vector, making it larger or smaller by multiplication. So I've pulled in two definitions here. Suppose we have vector u in component form and vector v also in component form. K, a constant representing a scalar. We know two things. We can add vector u plus vector v by adding the x, y, and z components for each. And then we can also scale a vector by multiplying that vector, say u, by some constant k. And essentially we would just distribute that constant across each of my x, y, and z components for that vector. Vector addition is really easy to visualize by using the parallelogram law. This first picture that I've brought in helps us visualize the sum of two vectors geometrically. So we have vector u, initial to terminal, and then we add to it vector v. So the initial point for vector v begins at the terminal point for vector u. These have a magnitude, a length, and then a specified direction. And the sum of u plus v gives us this pink vector, the resultant u plus v. So this is the resultant, this is the sum. So this is our geometric interpretation of adding two vectors. The parallelogram law is sometimes an easier way for us to think about this. So I've brought in a second picture, and this is another way to visualize the sum of two vectors. When we look at this, if we think of the vectors, and vectors are usually a force, but they can also be a velocity or a displacement. And thinking about them as a force, if you say we have two vectors acting on a point, and another thing that's helpful when we start drawing diagrams or thinking about these visually is to think about the vector as being a pull. So if this was our point that these vectors are acting on, we have one vector u pulling this way and v pulling this way. That resultant is formed by creating the parallelogram, right? So here's u and then plus v. So you can see that this triangle is the same as the triangle we have there. So the resultant is the diagonal of the parallelogram, which is created by the sum of those vectors. Addition is commutative with vectors. U plus v would equal the same as v plus u. So when we start thinking about the sum, these are the two ways in which we want to think about adding vectors. The difference of the vectors is going to be the opposite diagonal. So u take away v is going to give us this vector in the middle. And because that has to have not just a magnitude but also a direction, this vector I have just drawn crossing the opposite diagonal, that would be my difference of the two vectors, u minus v. All right, we don't deal with visualizing that as much, but u plus v is going to give us that diagonal using the parallelogram law, and we call that the resultant. And when we think about two forces acting on an object and we want to find the sum of what those two forces do, this is where we might end up using that parallelogram law. So let's look at applying vector addition and scalar multiplication to these component forms. In this situation, we're given vector u, -1, 3, 1, and vector v, 4, 7, and 0. We want to find the components. So for example, maybe we have 2 of u minus 3 of v. So 2 and 3 are the components, and then we're going to add or subtract those two vectors. And addition is the same as subtraction, it's just in the reverse direction, right? Adding a negative is the same as subtracting. So if I were to simplify this, I would write 2 times the vector -1, 3, 1, minus 3 times the vector 4, 7, and 0. So I can distribute that scalar 2 and -3 across those vectors, and that gives me -2, 6, +2. I'm going to go ahead and pull that negative through with both of these. So distributing the negative, this would become a plus. I have -12, -21, and 0. At this point, I would add my components. -2 plus -12 is -14. 6 plus -21 gives us -15. And 2 plus 0 gives us 2. So this is the new component vector. If I take 2 of u, 2 of vector u, and I subtract from them 3 of vector v. For our last piece here, we're going to look at this B example using the same two vectors, u and v. We've got the magnitude of 1/2 of the vector u. So if we looked at simplifying this, that'd be the magnitude of 1/2 times -1 times 3 times 1. I can distribute 1/2 to each of those components. I have -1/2, 3/2, 1/2. And then I would need to find the magnitude. And the magnitude is the sum of the squares of each of the components, and then we square root that sum. So I have -1/2 quantity squared plus 3/2 squared plus 1/2 squared. This is the square root of 1/4 plus 9/4 plus 1/4, or rather the square root of 11/4, or root 11 over 2. Now, magnitude is not a vector. Magnitude is the measure of length for this vector, for 1/2 of u. So that would lead me to believe that the magnitude of u would be root 11. Let's look at a couple properties of vector operations as well. Vector operations have many of the same properties for ordinary arithmetic. So if we have 3 vectors, u, v, and w, representing vectors in component form, as well as a and b represent scalars, we have these 9 properties. The first property is the commutative property of vectors, and we already mentioned this. U plus v would equal v plus u. 2 is our associative property. U plus v plus w is the same as u plus v plus w. So the parentheses are associating it differently, but we can still get that same answer. The identity property of addition, if you add the 0 vector, the vector does not change. Inverse addition, if you add the opposite vector, a vector plus its opposite is going to give you the 0 vector. Multiplication by the 0 vector gives you 0, or I'm sorry, multiplication by a scalar of 0 gives you the 0 vector. Identity with multiplication, if you multiply by a scalar of 1, the vector remains the same. And then we have an associative property here with the scalars and the vector. a distributive property. You can distribute a scalar across the sum of two vectors, as well as you can distribute a vector across the sum of two scalars. All of these properties are readily verified using definitions of vector addition and multiplication by a scalar. I'm not going to run through that for you here, but just know if you check any of these by trying to add, subtract, multiply two vectors, all of these properties would be true.